All right, so we've just started talking about chemical reactions, which are a way that we can change the identity of substances by combining two or more compounds together. Before we keep going with that, we really need to take a pause because there's a really important law that will govern how any reaction is going to work, and that is the law of conservation of mass. The law of conservation of mass states the following. It says that matter can neither be created nor destroyed. So, what does that really mean? Really, this just means three main things. One is that you can't make something from nothing. You can't magically poof something into existence. Number two is that you can't make something disappear. You can change what it looks like, but you can't just make it go away completely. And the last thing is really a summary of those two things. The amount of matter that you start with before a reaction happens will be the same amount of matter that you end with after the reaction. Put another way, maybe a little more simply, the quantity or the mass of the reactants that you have in a chemical reaction is going to equal the quantity or the mass of the products. In other words, the mass of the reactants, if it was 10 grams of reactants, for example, will give you 10 grams of products. It's not going to give you 9 grams of products. It's also not going to give you 11 grams of products. It's going to give you the exact same amount. So to prove this to you, we're going to use a reaction that's a really important reaction in our day-to-day lives, and that's the synthesis reaction that creates water. This reaction means that you need hydrogen gas and oxygen gas as your reactants, and that when you combine them together, you will create water as your product. Now, as it is, this seems like a straightforward reaction, but if you take a really close look at it, we'll actually realize that something is wrong. When we want to see if a reaction adheres to the law of conservation of mass or not, we actually need to count all of the atoms in the reactants and compare them to the quantity of atoms in the products, and we want to see if they match. We've got two different kinds of atoms in this reaction. We've got hydrogen atoms and oxygen atoms. Yes, they are tied up in these molecules over here, but those are the atoms that we're dealing with. And if we look in the products, we'll see that we also have hydrogen and oxygen atoms. So we didn't suddenly throw like a carbon in the products because there weren't any carbons over here. That wouldn't be possible because, again, you can't just create something that wasn't already there. So what we're going to do is we're going to go ahead and count the number of atoms of hydrogens and the number of atoms of oxygens in our reactants, and then we're going to count the number of hydrogens and oxygens in our products to see if they match. And if they match, we're good to go. So let's go ahead and start counting. So if we take a look on this side, we can see that we have 1, 2, or using our visual example, 1, 2 hydrogens. So I'm just going to put this little 2 right here. And if I count the number of oxygens, we'll see that we have 2 oxygen atoms as well. Again, with our visual example, we have 1, 2 oxygens. Yes, do we have 1 molecule of oxygen gas? Yes, but that molecule is made of 2 oxygen atoms. So that's the number of hydrogens and oxygens in my reactants. So now I'm going to go ahead and count how many hydrogens and oxygens I have in my products. So I go through the same process. I can see that I have 2 hydrogens here, or using my visual example, I have 1, 2 hydrogens. So I'm going to put that 2 right there. So far, so good, right? I've got my 2 hydrogens in my reactants, and I still have 2 hydrogens in my products. So far, things are looking good. If I count the number of oxygens, I see that I have 1. And again, using the visual example, I have 1 oxygen. So I'm going to put this little 1 right here. And now we have an issue. Because while my hydrogens have been conserved, in other words, they've been kept, it looks like I lost an oxygen somewhere along the way. Now you might be saying, okay, well then I guess this reaction just won't work. But you would be wrong. Because this reaction does happen. It just doesn't happen the way that it looks right now. Now you might be saying to yourself, hey, we could solve this problem. I'm just going to put another oxygen on the back end of this water, and voila, see, if I do that, now I've got my 2 oxygens, and everything is good. But if you're smart, you would know that you can't do this, because if you think back a couple of cycles ago, this is not water. This is a completely different molecule that doesn't look like this at all. So this can't be it, because this is the synthesis reaction for water, and that's what water looks like. Therefore, that can't be our solution, and we must have to do something else. So if I can't tack on an extra oxygen to this molecule, I need to use water. So what I'm going to do is, in order to get that extra oxygen that I need over here to show that the oxygen didn't just disappear, I'm going to add another water. Nobody said I couldn't do that. And what that does is now I have 2 oxygens, which means now I've got the right number of oxygens. And what that means I have to do is, because I needed 2 waters to do this, I'm going to show that I have 2 waters in my products, not just 1, because that gives me the right number of oxygens. Now you might be saying to yourself, okay, that looks great, looks like we're done. But you'd be wrong, because we kind of messed something up in doing this. If you look, yes, I have my 2 oxygens, but remember I added a whole nother water, which also has its own 2 hydrogens. So now if I count the number of hydrogens in my products, I don't have 2 anymore. Now I have 4, because I have 2 per water. I've got my 2 right here and my 2 right here. So now I have 4, which makes it seem as though I just added 2 hydrogens out of nowhere. But the law of conservation of mass tells us we can't do that. They must have been there somewhere. And if you're wondering, well, where did those hydrogens come from? They must have come from our reactants. So, similar to this situation, I can't just tack on an extra 2 hydrogens to this hydrogen gas. It's just not going to happen. But I can add more hydrogen gas. Remember, I need 4 hydrogens over here. So what I can do is add another hydrogen gas molecule. And if I do that, now I have the 1, 2, 3, 4 hydrogens that I needed. And to show this in the equation, I'm going to put a big 2 right there, because that shows that I have 2 of these now. All right, so did we do it? Did we actually make this equation work where matter wasn't created or destroyed? Let's take a look. I have 2 hydrogen molecules, each with 2 hydrogen atoms in them, for a total of 1, 2, 3, 4. In my products, I have 2 water molecules. Each water molecule also has 2 hydrogens, 1, 2, 3, 4. 4 hydrogens in my reactants, 4 hydrogens in my products. What about my oxygens? Each oxygen molecule has 2 oxygen atoms, 1, 2. So I've got 2 over here. Each water molecule in my products has 1 oxygen, 1, 2, for a total of 2 oxygens. Looks like we did it. So to review, the law of conservation of mass tells us that you can't make something from nothing. You also can't make anything disappear. What this really means is that whatever I started with, however many atoms I started with before a reaction, it's going to be the same number of atoms I end with. If we think about it in terms of mass, the same amount of mass that I started with before a reaction will be the same amount that I end with. So to put it quite simply, again, the quantity of atoms in the reactants, or the mass of the reactants themselves, will equal the quantity of atoms in the products, or the mass of the products themselves. And that's the end.